Hi, today's lecture is just going through module 4. So module 4 is going to be introducing ANOVAs and things like that, Kruskal-Wallis tests. So these would be analogous to, right, we did t-tests, we did 2 sample t-tests. The way you should think of an ANOVA is it's a multi-group t-test. So it's a version of a t-test that extends to 3 or more groups. One thing that we're going to want to know is, are the means different in each group? And if the means are different, which groups are different? So we'll do pairwise tests later on. So let's go look at our assignments. Here I've got the resources. I'm going to upload this lecture, obviously, when it's done. And let's go to, remember, as usual, right, here's our R code. And as usual, this is our data set for our R code. That actually should be a different data set. Let's see, M4L1 data. So I'm going to upload the correct one. So it should be an M4L1 data set. And I'll kind of walk through that. But as usual, what I recommend you do is watch this lecture, pay attention to the lecture, open up the R code, load in the data yourself, and just kind of play around with it a little bit. The R code will run. You can make slight adjustments to just kind of get a feel for those functions. I recommend you do that. Okay. So this is multi-group comparisons. So it's ANOVA and Kruskal-Wallis tests plus pairwise comparisons here. So let's say we want to test if the mean heights of males is the same in Shreveport, Lafayette, New Orleans, and Baton Rouge. So here we're going to let mu1 through mu4. These are going to denote the mean heights of males in the 4 cities. Analysis of variance, or ANOVA, you probably heard it called, test this hypothesis, which is that all of the means are equal and they're equal to some grand mean, versus the null is that H naught is false. So by H naught being false, it could be, right, that just the first group, so the Shreveport heights are different, could be just based on the New Orleans heights or the Baton Rouge heights or the Lafayette heights. So it can be false in a lot of different ways, right? It could just be one thing. It could be all of them being different. But the null here is that there's no difference in means across the groups. So no difference in heights of Louisiana males across cities. So first thing we should do is just kind of look at a box plot. And there's some code in the R code how to do that box plot we can look at after together. You can see right here, I've got weights. These are weights that I'm testing. And you can see that New Orleans males, at least in this hypothetical data set, way more than the rest of the city or west of the state, and Shreveport way less. So you can see that in these box plots. So, you know, probably what we'd expect to see before we do any statistics is that the ANOVA would recognize this difference here, and would hopefully we'd recognize that New Orleans was higher than the rest of them and Shreveport was lower than the rest of them. So let's kind of get how would we do this experiment. Well, I'd go around and I'd randomly sample males from each of these places. So I'd go door to door. Hey, is there a male in the house? Oh, yes. Okay, can I get your height? Sure. So I'd sample that randomly. So I could get, right, in 1 observations from Baton Rouge, in 2 observations from Lafayette, and 3 observations from New Orleans, and in 4 observations from Shreveport. And I can get averages from all of these, right? So here I have these sample sizes in each city. They can be different. They don't have to be the same size in each city. And basically what this model assumes is that each data point that we collect here, every single one of these are normally distributed and have some mean mu k and a variance of sigma squared. So it is a parametric model. ANOVAs do assume your data is normally distributed. So if you have a very small data set, generally not recommended to use ANOVA. So this is what the F test looks like. So just some notation. NK is the number of observations in group K. Capital K, that's the number of groups, and capital N is the total number of observations. It's just summed in each group. X bar K is the average in group K, and X bar is the overall average, disregarding groups. So the between group variation, you can write like this. The within group variation, you can write like this. So the way to think about it here is this X bar K minus X bar. This is how much the means in each group vary from the overall mean. So you can imagine, right? It's like assessing the difference between like this line and what would happen if you just pulled everybody together. So that's like how much does each group vary from the overall population mean? And this within group variation, this is just basically within each group, how much does each data point vary from its mean within each group? I'm not, again, as usual, I'm not crazy concerned about, you understanding the formula. I just want you to kind of understand these kind of ideas. So the idea here of an F test and ANOVA is that, if the means really don't vary, like if they are the same for each group, then the variation of the means around the population mean and the variances of the data around each group mean should be about the same. So if we took a ratio of these two things, should be about 1. That's the idea. Okay, so again, right, between group variability, it's the variance of the means of each group compared to the overall mean. And within group variability, it's the total variance in each group summed across everything. If the group means don't differ, then the between group variability should be similar or smaller than the within group variability. So this is the F test. It's just those two divided by each other, the between group variability over the within group variability. And again, the idea is if the data really is normal, which we're assuming, and the means are all the same, then this ratio should be 1 or even really small, right? The bigger that this numerator is, as far as the distance of each population mean, each group mean being from the average, that means that they're more spread out. The averages are more spread out. So this test statistic follows an F test with K minus 1. K is our groups, and N minus K, that's our total number of observations by minus our number of groups, degrees of freedom. You've probably seen a table for this. You don't have to use it anymore. We're just going to use R to get those values. So when you get output using ANOVA, this is the kind of output that you'll get. We can go look at this code after and just kind of walk through it. Here, what you'll get, I'm testing this example here. So I actually have the data here. I'm testing, do weights differ by city? And I'll just show you what the output looks, and we'll go back into the code and do it ourselves as well. So here I've got a degrees of freedom of 3. That's because I have 4 groups. So 4 minus 1, that's this K minus 1 here. This N minus K, this is going to be the total number of observations, which is 200 minus the number of groups, which is 4. This is those between group variances. This is the mean square. That's this, the top, and the bottom, this is the bottom here. And then I get this F value and I get a P value here. So again, the P value is the probability of getting a test statistic as extreme or more extreme than 294 if the null is true. So it's more or less, it's not totally correct, but you can think of a P value as the probability that the null is true. That's not completely correct. Again, don't go around saying that, but you can think about it that way. The smaller the P value is here, the more evidence that your null is false. So here, this P value is very, very small. It's below 0.05. Remember, e to the negative 16 means that it's got 16 zeros and then a 2. So it's tiny, 0.000000000000002. So we reject the null here, which we reject the null that the weight is different or the same between the 4 cities. And you can see that visually, right? That there is a big increase in New Orleans and a big decrease in Shreveport. Okay, once we get a significant hypothesis test, usually what you'll want to know is, okay, I know that the weights are different across these 4 cities. Which cities have different weights? So I can use pairwise comparisons. I can use 2 sample t-tests here, and it'll tell us which groups have statistically different means. Now, this involves multiple comparisons, right? So if I have 4 cities, Baton Rouge, Lafayette, New Orleans, and Shreveport, and I get a significant difference, then I want to compare maybe, do Baton Rouge and New Orleans differ? Do Baton Rouge and Lafayette differ? Do Baton Rouge and Shreveport differ? Do New Orleans and Lafayette differ? Do New Orleans and Shreveport differ? Do Lafayette and Shreveport differ? So that's 6 comparisons that I want to make. Now, one of the things about type 1 error here is if I use a 0.05 for my type 1 error constraint and I make 6 comparisons, then your type 1 error is going to be potentially 6 times 0.05, which would be 30%. So sometimes people will use Bonferroni corrections here, which basically they have the number comparison. So in this case, 6 comparisons, and you'll divide your alpha level, which is your type 1 error, by those comparisons, by those numbers. So from a Bonferroni correction perspective, if I want to like be conservative about testing pairwise differences, you take that 0.05 and you divide it by 6, which gives you what? 0.08, something like that. 0.05, actually, let me just tell you. So that's 0.05 divided by 6 is 0.008. So I'd be looking for a p-value to be below 0.008 for significance using Bonferroni's correction. Another way that people approach this is Fisher's least significant difference. So basically, if you see a significant result, then you can just use the same alpha level. So you can do a pairwise test between Baton Rouge and Lafayette. And if the p-value is less than 0.05, you can assume that there's a significant difference. You could get higher type 1 error here, incorrectly rejecting a pairwise difference. There are other ways to do this: Chef's method, Duncan's method, Tukey's method. I see these less in literature than Bonferroni's or Fisher's. Honestly, it just kind of depends what you want to do here, how difficult, like how bad is a type 1 error. This is just kind of observational, right? But you can imagine if you incorrectly reject a pairwise difference, that could cost your company millions of dollars or something like that. If that's the case, maybe you want to be a little more conservative and do the Bonferroni correction. So we'll just come look at the data again. So again, right, now that I know that there's significantly different weights by city, I might want to know, hey, do New Orleans and Shreveport differ? Do New Orleans and Lafayette differ? Probably Baton Rouge and Lafayette don't differ. You see these box plots are really close to each other. So I can do this. I can use pairwise comparisons with t-tests here. This is my p-value here for the Bonferroni is 0.05 divided by 6. That's 0.008. Where did that 6 come from? Because there's 6 pairwise comparisons I can make. And if I go look at the data points here, I can see that Baton Rouge and Lafayette, this p-value is pretty big, right? So I don't reject the null that Baton Rouge and Lafayette have different mean weights. You can see that here too, graphically. But the rest of them, I will reject the null. So New Orleans has significantly higher mean weights than Baton Rouge, than Lafayette, and then Shreveport. And Shreveport has significantly lower weights than Baton Rouge and Lafayette. That's how you read this. You see how it's a matrix. The rows are the city, the column or the city it compares to. It doesn't make sense to compare Lafayette to Lafayette, right? And then it doesn't have a line here for New Orleans because we actually get this New Orleans Lafayette comparison here in the second column, second row. A Kruskal-Wallis test is pretty much exactly like an ANOVA. The only difference is it's a non-parametric test. So this is better with small sample sizes. It's an extension of the Wilcoxon-Mann-Whitney test to 3 or more samples. So we talked about the Wilcoxon rank sum test last time with 2 samples. This is just extending that to 3 or more. Here, the null is just, instead of that the means are the same, it's that the medians are all the same. And the alternative hypothesis is at least one set of medians differ here. Okay, it is the assumptions here. It's non-parametric. It does not assume that they're normal. It just assumes that all the distribution shapes are somewhat similar, which I think is relatively fair to assume for the most part in small sample sizes. So again, it's just a direct extension. In the background, what it happens is it takes all the data of the 4 cities or however many you have, sorts them all together, and then tries to figure out the order of all the data points in the combined sample. So, you know, if, for example, all of the Shreveport weights are the lowest, it uses that ordering structure to get the idea. This test statistic here follows a chi-square distribution with k minus 1 degrees of freedom. K here is the number of groups again, and larger values indicate the city heights are more different. Yep. So this is what the output would look like in R. You can see this is our test statistic is 159.91, and this is our p-value. Our p-value is really, really small. So again, our null is that there are no difference in median heights, and since we reject that null, we can assume that there is some statistical difference by height here. So the median differences, the median weights are significantly different by city is our conclusion based on this p-value being very small. Pairwise comparisons, I can still do either a Bonferroni adjustment, or I can just kind of ignore that adjustment, take the type 1 error increase and use Fisher's least significant difference. Some people, so there's two schools of thought on what to use for a non-parametric test. Some people use t-tests with an adjustment based on the Kruskal-Wallis. To me, I think it's more appropriate to use a Wilcoxon rank sum test, because if you're doing a non-parametric test for overall differences, probably makes sense to do a non-parametric test for pairwise differences afterwards. So you can just do a pairwise comparison of each sets of cities in those that there. Multi-group, I can still use chi-squared tests and Fisher exact tests for independence with categorical variables with more than 2 categories. There's just no odds ratio whenever you have multiple groups. Okay, so let's look at an example data. So I've got this data set M4L1 that I'm going to upload. So this is data that consists of treatment, which is whether or not patients received aspirin, blood pressure 1, which is the blood pressure of each patient before taking treatment, blood pressure 2, which is blood pressure for each patient after taking treatment, and cancer stage, which is 1, 2, 3, or 4. And the goal we want to know is, do blood pressures differ among cancer groupings? So this is just me kind of reading in the code here. Okay, so I'm reading in the data. I've got this users, HAP, desktop, work, LSU teaching, BSPM program module 3. That's where I have this data set saved. Here's my data. I'm reading it in M4L1 data.csv. I'm looking at the data using the header. Here I've got my patient ID in the left column. I've got my treatment, 1s and 0s. I've got my blood pressure 1, my blood pressure 2, and I'm cancer stage. So maybe I want to know, does their first blood pressure differ by cancer stage? The first thing I might do is I might just plot this. So data $, blood pressure .1, and I put a tilde cancer stage. If I'm using box plot, R just knows, hey, look, he wants to do a box plot by cancer stage. I've got my title, I've got my X label, and I've got my Y label. So if you look at this box plot here to the right, it doesn't look like there's a big difference in blood pressure by stage, but is there a statistical difference? So we can actually test this pretty easily. The easy way is just use this command here, AOV. So I'm saying, hey, R, I'm defining this object called AOV. It's an ANOVA. It's going to store the results in M1. M1 is now going to contain my results. And you notice the syntax looks just like a box plot. So I say data, blood pressure 1, tilde, data, cancer stage. And then I'm taking the summary of M1. So here I see, okay, look, it looks like overall I had 3 degrees of freedom by cancer stage, because I have 4 groups. 4 minus 1 is 3. I had 100 data points. So my sum of squares residual is 96. And really all you need to know is this p-value here. So this p-value is 0.101. Which means I fail to reject the null that the mean blood pressures are different by group. I can use a Kruskal-Wallis test just as easily. Just swap out the AOV for Kruskal.test. This is using a non-parametric test. And you can see the p-value here is 0.22277. So I fail to reject the null that the mean blood pressures or the median blood pressures are different here. So that's based on the ANOVA and the Kruskal-Wallis test. Yeah. So another example, does blood pressure decrease depend on how high blood pressure was initially? So I can look at different groups here of less than 160, 160 to 180, and then over 180. So all I'm doing here is, this is just a histogram of the blood pressures. You can see that here. So the 160s are going to be everybody to the left, 160s to 180s are going to be everybody here, and over 180 is going to be everybody to the right. So I'm just creating this variable here. So I'm creating a BP group variable. I'm saying, hey, I want to repeat 160 to 180, the number of times the data. And then I'm going to say, hey, look, all the BP groups where I have a blood pressure 1 under 160, replace that value with under 160. And hey, all BP groups with blood pressure over 180, replace that with over 180. So this is, how you set those up. So I'm going to plot them, right? So I created BP diff. This is the difference in blood pressure, second blood pressure minus first blood pressure. And I'm going to do box plot of BP diff by BP group. So BP group I made before, right? So you can see the box plots here. It does look like if you had a blood pressure over 180, you were more likely to lose blood pressure. That's what this is saying here. Your second one was bigger than your first one, or your first blood pressure was bigger than your second blood pressure if it's negative. So you could see a shift here, and I can do an ANOVA. M1 is my ANOVA blood pressure difference by blood pressure group, and I take the summary. I can see this p-value is very significant. So what does that mean? That means that the mean blood pressures do differ by initial group, by initial blood pressure group. So there are differences, and I can do this via Kruskal-Wallis test too. So Kruskal.test BP diff by data BP group. This p-value is also significant. So both the ANOVA and the Kruskal-Wallis test said that there were differences. So the ANOVA says that there are significantly different blood pressure differences by initial BP group in terms of means. And the Kruskal-Wallis test said that there were significantly different medians in terms of that difference. Now, after that, I might want to look at a t-test. So do t-tests by each group. This would be an ANOVA pairwise. So you can adapt your code to do this. Here's what I'm saying. I'm saying, hey, look, do a t-test. Remember t-test, right? Help.t-test, we can plug in X and Y, or we can plug it in via formula. So here I'm plugging in via formula, and I'm saying, hey, look, I want to only look at the blood pressure groups 160 and 180, 160 to 180. And so I'm telling that here in the group. So I'm doing tilde group. Just imagine I've basically created two vectors, which are subvectors of the data. It doesn't have the full data structure anymore. So this t-test here, this p-value is 0.002. Difference in means is not equal to 0. This is my 95% confidence interval on this difference in means. So there's a significant difference between 160, less than 160 and 180 to 160. Here I'm looking at less than 160 and greater than 180. What I would encourage you to do is just adapt this code to whatever group you're looking at when you're doing pairwise comparisons. So just manually do this. This is the easiest way to do it. So just take this code, whatever your new variable is. Let's say you're looking at differences in race. You'll change BP group to race. You'll change BP diff to whatever the name of your variable is you're interested in. And you'll have to index the races separately in these two. So I can see a significant difference between these two groups too. This is 160 and 180. And then last I've got 180 to 160 to 180. And this p-value is also significant. So all these p-values are very, very small. And I would reject the null whether I use Fisher's test or Bonferroni's adjustment here. Kruskal-Wallis pairwise, it's the exact same syntax. All I'm going to do is replace t.test with Wilcox.test. That's it. So for comparing less than 160 to 160 to 180, this p-value is very small. Comparing less than 160 to greater than 180, this p-value is very small. And comparing greater than 180 to 160 to 180, this p-value is also very small. So I would reject the null after I see that there's a difference overall. I can say that all three of these means differ significantly, medians. And you can see that, right? There's a clear shift. So here, not only do the means differ across the three groups in terms of blood pressure loss, and the medians differ, but the medians differ between each and every pair of groups. So this median and mean is significantly different from this one. This median and mean is significantly different from this one. And this median and mean is significantly different from this one. Independence. So this is a multi-group test of independence. This is categorical data. I can just table things together. This is cancer stage and BP group. So maybe I want to know that do these differ? Are these independent of each other? And I can do chi-square.test and just plug them around that table. This gives me a p-value of 0.28, which means I do not reject the null hypothesis of independence, which means I can assume, at least for now, that the blood pressure groups in the cancer staging is independent based on the data I have. I can use a Fisher exact test in exactly the same way, instead of a chi-squared test. And here I also get a p-value that's fairly large here. You see this error here that you get from the chi-squared test. When you get this error, just by default, switch your test to a Fisher test. It's an error. Sometimes the results of your chi-squared test can be misleading whenever you have that error. And that's it. So yeah, I don't know. We can go look at the code. So here I have my R code. I actually have this, saved in the same file. the data location. So I'll adjust the one here. So this is the file we have. I'll just walk through everything again to make sure everybody's on the same page. I'm going to read in my data. This is my data. Oh, did it not run? Module 3. I can't change my working directory for some reason, probably because it's not the right. It's just going to be module 3. This is it right here. Let me just make sure I have this. Don't know why that's not working. So I'm adjusting this here. Module 3. Guess I'd change my file names at some point. So here I've got my data now. I can look at my data. This is what my data looks like. This is that box plot syntax, right? So I'm just looking at the first one by cancer stage. I can look at the data too, data, cancer stage. Okay, I can do a tabling just to kind of see the info. This is my box plot. I can zoom in on it if I want. If I want to use ANOVA, I just do the same kind of syntax, just like a box plot. If you just run it, you'll get results here. I can also put a summary around it like this. I just like to define it as a name because they don't give you this p-value, at least initially. So if you define it as M1, now M1 has this result. So I can see, oh, look, M1. But what I really want is a summary of M1. I really want this p-value. And again, that p-value says that the blood pressures do not differ by cancer stage. Using Kruskal-Wallis test, I can do the same thing. Kruskal-Wallis test actually gives you the p-value right away. I think if you pass a summary over it, it doesn't actually do anything. I can double check. Yeah, so you don't want the summary for the Kruskal test. For some reason, you do for ANOVA. So if you run this here just without the summary, you can see the results. That's your p-value. And that's comparing whether or not blood pressure is the same here. So all this code is doing is creating these blood pressure groups. I can look at it, right? So first line is just going to create all the same blood pressure group. This rep command is just basically saying, hey, look, I want you to repeat this character string 160 to 180 in row of data times. Say table data BP group. You can see that here. This is my BP group. It's all 100 right now. And then I'm saying, hey, look, find all the ones where the first blood pressure is less than 160. This is going to turn into trues and falses. Right now, this is what they look like. They're all 160 to 180, but I want to replace them with less than 160. Do the same thing for less than 180. Now, once I do that, I can look at my BP group. Here I have all these values. I can calculate the difference here. That's what this line does. So BP diff's not a thing now. Now it is. I can say summary data BP diff. Here we go. I've got a summary of my data points. Then I can do a box plot. I can do an ANOVA. So you can see the ANOVA here. I ran this line and summarized it. Again, you have to do the summary on ANOVA. I get a very small p-value, which means I reject the null that these are equal in terms of means, and you can see that. I can see which ones differ. So again, how am I doing this? Basically, this is going to pull out only the BP diffs for people with a BP group of less than 160 or 160 to 180. Let me get the whole line here. That's just how I'm indexing this. So these are all those data points, and this is the blood pressure group of only those blood pressure groups. So I have to index both of these. So notice how it's only pulling out the 160s and 180s. These are also the same length, right? So this is 58, 59, 60, 61, 62, 63, 64, 65, 66, 67. And this is 64, 65, 66, 67, 68. They're both the same length here. So that's why I'm indexing that. This is just a 2-sample t-test. So this p-value is very small. So I assume that they differ in these two groups. Same thing here. This p-value is really small. So I assume that they differ. And here as well, the p-value is really small. Now here it doesn't matter, right? Whether I do a Bonferroni correction or a Fisher's LSD, because the p-values are both below that. But just as reference, right? If I have a 0.05 level, I have 3 groups here. So I'd want to do 3 comparisons. So my Bonferroni p-value would be 0.016. So I'm looking for p-values for the Bonferroni correction that are below 0.1016 compared to 0.05 for the Wilcoxon. For the regular, this is the Kruskal test, BP diff by data group, BMI group, and then I can do the same thing with the Wilcoxon test. So I see the Wilcoxon p-values are all also really small. So let's go look at the homework real quick. And I'll again upload the new lecture there. So this is the assignment. So for this assignment, you're going to use the chicken weight example. It's from I wasn't going to get up a midterm, but I decided not to just because we already have a lot in this class and we don't have a lot of time. So this is the data set you want. You can basically get this. You can use the R using the command data chick weights, and then that'll give you the data set. The data set consists of 6 feed types and the weights of chicken after being fed for a month. So let's just go to R and I'll just show you. I could say data chick weights. So now I have this data set, and if I want to define it like as capital data, I can say chick weights like this. So here I have my data, See here I've got weights and I've got the different feeds. So for example, I can do a box plot, data weight by data feed, just to get an idea of what this looks like. And this is what my data looks like. Okay, so this is a box plot by weights and feeds. So obviously we're going to want to test, are there differences in these means? So I want you to plot a box plot, which I just showed you. So you're going to at least add like nice labels and things like that. You're going to do a ANOVA based on feed type. What are you testing and what's your conclusion? You're also going to do, if there's a significant results, you're going to compare the sunflower fed chickens to all other chickens using a t-test. So again, these would only be the ones you're going to compare sunflower to soybean, to meat meal, to linseed, to horse bean, and to casein. So you're going to want to use this kind of indexing here, right? So like, table data feed. You're going to want to look at, for example, you're going to want to do an indicator that looks like data feed and see sunflower and soybean to make that comparison. You're going to want to use this kind of indexing just like this up here for those t-tests. And you're going to want to do all 5 pairwise combinations. Using a Bonferroni correction, what would be the threshold for significance? So here, right, alpha is 0.05. I have 5 comparisons, which means the Bonferroni correction, I'm going to check all the p-values against 0.01. Would any conclusions in number 3 change if you use a Fisher's least significant difference, which is a type 1 error 0.05 instead of 0.01? Next, you're going to do a Kruskal-Wallis test. So instead of ANOVA, you're going to do a Kruskal-Wallis test. What are you testing? Okay, so the ANOVA, what's it testing different from the Kruskal-Wallis? They're slightly different, right? But what are they both testing? What's your conclusion? And then if there is a significant result, compare the casein fed chickens to all other types. So that's a different type, right? The casein chickens, that's these here. You're going to compare all these weights to the other 5 types. If you use a Bonferroni correction, right, what would be your threshold for significance? You're making 5 comparisons. What's your conclusion? Would any conclusions in number 6 change if you use Fisher's least significant difference? That's the whole assignment. So I think it's pretty straightforward. I encourage you to get started early and ask questions early and often. All right. Hope everybody has a good week. And if you want to come to office hours, just come on in and you can give me a heads up. You can also shoot me an email if you have any questions.